donde marcas el con la figura de...
Ah, vale. Okay, so I think we can start already. Borja will do the short introduction.
All right, okay, welcome everyone. Sorry for the 5 minutes delay, there were some technical problems. So today we have Inès Amestoy. She's a PhD candidate to this government of Aragon fellowship. We sent all the paperwork last week, so fingers crossed, and see if we get lucky, and she will join us. It will be great. We have also Pedro Pablo. He's also he was doing, well, first of all, Inès was studying at the University of Toulouse. I didn't prepare that, so Joe just told me, can you introduce the speaker? So I just like trying to remember everything. She studied at the University of Toulouse, and she has been doing an internship at the IEC. She's working mainly with Olbeck and Diego Godoy Rivera in binary stars, a lot of asteroseismology she's going to talk about. And Pedro Pablo also, he has been working at the IIC. He has been doing exoplanets, what he's going to talk today. But also he got a PhD position in University of Cadiz to work in SuperNovae, and he will be the first gentleman that getting a PhD in astrophysics at the University of Cadiz. So I think it's remarkable. All right, guys, all yours. Welcome.
Thanks. So hello everyone, my name is Inès Amestoy, and I'm going to present you the subject of my internship that I did at the IEC. So it's about finding the sweet spots, modeling of oscillating with giant binaries. So I was supervised by Olbeck and Diego de Rivera, and also I collaborated with a few other people at the IEC and also at the CA Paris-Saclay. So in stellar physics, one of the main objectives is to calculate the mass of a star. And the mass of a star is the age of the star is highly reliable. The age of a star is depends a lot on the mass of the star. So this is not only important for stellar physics, but also a lot of other fields in astrophysics. For example, galactic evolution. In order to characterize the age of a galaxy, we need to constrain the age of the star that composes the galaxy. And it's the same thing for exoplanet characterization, because the more we constrain the age of the whole star, the more we can more easily the exoplanets around. So, since I talked about mass of a star, I will give you a few definitions. For example, we have dynamical mass. It's about orbital mechanics. For example, it's based on the equations of Newton and Kepler's law. And it's highly reliable when the orbit is constrained and independent from stellar models. But since I mentioned an orbit, this is only computable with binary systems. So it reduces a lot the sample of the star from which we can obtain the dynamical mass. But fortunately, we have another definition of the mass that is a seismic mass. It's based on the astroseismology of Shoreline oscillators, and it's applicable for all low mass stars, so type FJK. So we expand a bit the sample of the stars, and it's also independent from the inclination. But the main thing is it depends on scaling relation that I will introduce later, and we need long time series data. So we have drawbacks and advantages for each definition of the mass. So since we have two of them, let's compare them. Here in this view, we can see the comparison between seismic mass on the y-axis and dynamical mass on the x-axis. So the first thing we notice is that there is discrepancy between both of them, because the ideal case would have been to have all the dots in the y equals x-axis. It's not the case. We see that the seismic masses are a bit overestimated compared to the dynamical masses. And also we notice that this is a very small small sample. We have only 10 systems here. I mean, this was the paper from 2016. Now we have a bit more, but 15 is not that much. And the main reason is that these systems are located here at the intersection of three properties. There are binary systems first. Eclipsing binary system, it means that we see them edge on. And also one of the two components must be oscillating in order to get the seismic mass. So we have only 15 benchmark systems, and the main objective of my internship was to study the following one. So this is the name. This is the official name of the binary system, and the nickname was EDFX. So it's a binary system that is located over here in the HR diagram, so in the red plum. And so this is the objective of the internship. So EDFX has been discovered by Gaia in 2023, and this is here the first light curve that has been extracted for this target. So the first period that was given by the Gaia collaboration was 3.8 days. So we see here the quite sparse light curve with the 3 bands of Gaia. And then this data have been completed by TESS data. And we can see here a huge difference. We see first that for only the Gaia data, we missed completely 1 or 2 eclipses. So this is why only from the Gaia data, it was only a candidate. Now with the TESS light curve, we see it's confirmed that it's a double, that is an eclipsing binary system. So what's happening there? In the first, the deep eclipse, we have the red giant here. That is in the front, and let's call it the companion in the back. And then the other eclipse, the more shallow, is the other way around, the companion in the front. We can talk about the shape later. And the new period given by TESS with this more complete light curve was 65 days. So first of all, this was literature. Now, in this part, I will talk about the work that I did, and it was based on observations from the Las Cumbres Observatory. So it's a network telescope all around the world. So there are 100 telescopes with NRS, the network of robotic spectrographs, so high resolution spectrographs, and EDFX has been observed by 2 of the telescopes, one in Chile and the other one in South Africa, during the guaranteed observed time of the IAC. So I got access to spectroscopic information. Here, this is the very first plot that I did for this target. So the spectrum here is for one observation of the target. And I had to study the stability of this data, if it's reliable or not, in terms of radial velocity as well as wavelength. So here we see the wavelength stability here. So between 2 spectra, I had access to 26 observations in total. And from them, I got this stability in wavelength and this one in radial velocity. And we will see here, we see here that compared to the typical binary amplitude, that is not very, it's much smaller. So we can say that the instrument is stable and we can trust the information that we get from the spectrum. So after the raw spectrum, I got to work on the correlation function. So this is very useful for binary systems. It's a mathematical concept that compares two signals. For example, if we have a reference spectrum from which we know everything, and another spectrum that is one of the targets, we let's imagine that we have the two spectra. We will compare them, and then when the similarity is at its peak, we have a peak in the oscillation function. So, for example, here the peak corresponds to the radial velocity of the target, since the reference one is at rest. So this is for one observation. Again, it was done over and over for all of the observations. So what do we see here? Here we can see the peak of the highest peak, let's say here, and the maximum of each one is represented there. I will talk about just later how I got from this to that. And now if you take a closer look, we can see here at antiphase that we have linear bumps here, and it follows over that. Actually, it's the signal of the companion. The highest peak is the red giant, and the other one that is represented here is the companion. So we see this double helix shape that actually confirms that it's a double-line binary. So double-line binary system is a system where we see the contribution of both components in the spectrum. So these two bumps mean that in the raw spectrum, it was not visible before, but trust me, we can see the influence of the giant, of course, because it's the more luminous one, but also the other one, the companion. So this is a double-line binary system. It's official. And then just to give a comment of how we got to these points, I did a double Gaussian-Lorentzian fit. So I had to divide the work and iterate the work because I tried to do the double Gaussian, the double Lorentzian directly. It didn't work because of the kind of strange shape of the double peak, because it's a small contribution. Even if it's here, it's a small contribution. So I fit the first peak that it's very well constrained, and then I subtracted it in order to get the second one. Again, this is not an optimal way of doing it, but I was only interested on determining the peak and the intensity more or less. But it wasn't, for a first study, the results were quite good. So these are the results basically of the spectroscopy, a double-line system with radial velocities, and we saw that the orbit is well covered. Also, all the orbit is well constrained. Now, let's go back to the dynamical mass. So all this work before has been done in order to get the first of the two masses, the dynamical one. So in this equation here, this is the mass that we want. The K2 and 1 are related to the radial velocity. And then we have constant here, the period that was given by the article of Paul, the eccentricity and the inclination. So the K, E, and I are the unknowns. And this is the next step. I got to model the system with PB. And this is the data that I used. For example, here, I didn't use the Gaia data because it was too sparse and we wouldn't get into any more information than the test curve. And I got, obviously, the orbit curve. So I got to use the physics of eclipsing binaries software in order to fit both of the data sets. And the interesting thing with Phoebe is that it's not only solving the RV and then solving the light curve, it's a combination of the two of them. Because, for example, the eccentricity and the inclination depend on both of the curves. So this is the intermediate results, let's say, the inclination, the mass ratio, eccentricity, and both, the period that we already had. So with all of this, we see that the orbit is well constrained. And this is the result that we have: the mass of the red giant and the companion, the dynamical mass of each one. So 1.46 and 1.37 solar masses. So now we have the first part of the work. And then let's go to the seismology. So this is what is called a poor spectral density. It's basically the light curve. It's from the TESS light curve, the same as before, that has been transposed to the frequency domain in order to get this PSD. So this work has been given by the two researchers at the CEA of Sabatier. So from this, basically, we get to have a first computation of the seismic mass. So this is the scaling relation that I talked about before. It's it relies on nu max that corresponds here to the maximum of this little bump, and the delta nu, so another frequency, that is, if we zoom here, the delta in frequency that we see here, and the effective temperature. The effective temperature was given by Gaia, so this is why we have here the one important uncertainty. And from this, I mean, first approach computation, we have the seismic mass of the red giant, so 1.3 solar masses. Here we notice that we don't have the seismic mass of the other one because or it doesn't oscillate, or we don't see it with the instrumentation yet. And so this is still, I mean, this was still work in progress because it's a first approach. And there are new sectors of tests that are coming that can complete the calculation here. So to summarize, we see here that we talked about the three symbols here. I recall here the results of the dynamical and seismic mass for the red giant because this is the only one we can compare. And we see a delta in mass of 11%. So it's still a work in progress. And we can add it to the very first figure that I showed. So we see here two things. First thing, this is still not on the y equal x-axis, obviously. And also we see that it's not even on the tendency of overestimating seismic masses. So we have to be careful about these results. But again, it was for an internship, so this is the result I got for 5 months of work. And nevertheless, we can see some axes of improvement. We can constrain the temperatures from another method because here, for example, in the Phoebe modelization, I cannot constrain the temperature of each one of the components. I cannot only constrain the temperature ratio. And I use the one from Gaia because this is the only variable that I have. And it can be determined with spectral disentangling. So in a few words, it's a method that decorrelates the influence of each star from one spectra to extract the spectra of the red giant only and the spectra of the companion only. And I could also use spectroscopic parameters in the Phoebe model. And computing the errors by modeling them is part of the process of Phoebe. Actually, Phoebe works in 3 steps. The first one is like initial guesses. The second one is computing the values. And the third one would have been to compute the errors. But it was very time consuming. I mean, the second step was time consuming, but the third one even more because it was based on the Monte Carlo. So it was far beyond the scope of this work. And also here, the CCF has been extracted from the LCO data. There was a file CCF, the file spectrum. So I didn't go further. I just get to use the CCF given by the LCO. But the template of LCO didn't take into account that it was a binary system. So it was like a fit for a single star that I didn't use for a binary system. So by performing a CCF by ourselves, we can improve the model. And this target is also very interesting because it's the first and only known to date eclipsing binary system oscillating a red giant in the place of field for the moment. So, as you may know, PLATO is an ESA mission that will be launched late 2026, and it will work on the search for Earth-like planets on one side and also stellar oscillation from one side. So it has, let's say that this target, in effect, has a bright future ahead of it. So thank you for listening.
Everyone for the talk? Questions?
Yeah, I have two questions. Thanks, Inès, for the presentation. What is your guess about the offset between the dynamical mass and the asteroseismic mass? What do you think is causing this offset?
For in general, or for the target that I...
In general, what is the physics behind what do you think is driving the discrepancy between the dynamical mass and the asteroseismic mass?
In general, in the
Yes,
whole
yeah.
My guess is that, I may be wrong, but the thing that asteroseismic masses rely on the scaling relation that I talked about before, but it seems very general. And also, here the scaling relation, the determination of the parameters is not easy. And this one, the second one, is harder to determine because this delta mu changes over the spectrum. So the uncertainty here is propagating and may lead to an approximate value of the seismic mass. But the thing is, the sample of the star that can from which we can have the seismic mass is still small, so we cannot confirm that this is the absolute truth about the calculation of seismic mass.
Yeah, I have seen that also some authors, they have been trying to understand the effect of the metallicity in the scaling relation. So probably it's incomplete. Right?
Yeah. It's only. I mean, it seems a bit approximate. This is why even in the articles, it's approximately equal to. So I think this may be because, for example, the determination of the dynamical mass, since the dynamical mass is something like Newton's law, Kepler's law, it's something that is more difficult to put in question. That's it.
In the previous slide, the uncertainty is 0.4, so I don't think there is a discrepancy. To me, they are very well consistent, the dynamical and the seismic mass. Given the uncertainty, I think it is well within the correlation.
Yeah. It was a bit more like the overall tendency, let's say. And maybe one of the solutions would have been to put the uncertainties as well, but I didn't find them for all of them.
It seems like there is a systematic in other studies between the masses. It's something that you do in your study that it's markedly different from what they do that could fix that systematics.
Yeah, I think with all the artificial improvements, I mean, I saw here in the work, even when I talked to my supervisors, we were like, okay, this is the value, but we know that we can do better. For example, in all the aspects, in the seismic aspect and also in the PV modeling. But we didn't have a more amplitude to dig into the, especially the PV modeling. Yeah.
More questions? Okay. No? Thank you.
Thank you.
¿Dónde?
El láser arriba.
Vale, perfecto. Es que hay muchos plots. Well, I'm Pedro Pablo Mini Gallardo, and I'm here to present how did we determine by an empirical way the cosmic shoreline. I make it with the help of Enrique Paller and working with IAC. Well, the first thing is what is the cosmic shoreline? That I don't know if you are related to this term. Then how did we redefine it? What's the impact of this concept? And then the conclusion of the work. First thing, this is the first time they plotted the cosmic shoreline. This is a way to organize planet in retaining and non-retaining atmosphere. So under this, okay, I know this plot is a madness, but it is what it is. Here we have solar system objects. Here we have the sample of planets that were discovered in 2017. Here we have some tiny planets, dwarf planets, and everything. And these are also dwarf planets, solar system items, and everything. Here it's almost impossible to see anything, so we try to make it clear. Well, this is currently updated because this line, okay, here you can see the mathematical relation. You have the classic relation between the cumulative insolation, which is the radiation during all the history of the star, to the planetary system, the escape velocity, which is a simple magnitude, and the relation is to the power of fourth. And the problem is that by this relation, we miss the 0 point quantity. So the thing that they found easier is to determine the 0 point using Mars. So here, where is Mars? I lost it. Here. They use Mars to determine the 0 point for the line. But in our study, we saw that, okay, maybe with the new discoveries in atmospheric characterization, we find out that a lot of planets get out this thing. Another important thing is that now that we have this instrumentational gap between instrumentation in exoplanets and what we want to find in exoplanets, we have to determine what planets are interesting to observe if we want to find these sub-Neptunes and super-Earth planet life. So here there is a plot from this year from Emily Paz and David Charbonneau and Andrew Vanderburg, where they recalculate the cumulative insolation of N-bar planets, of N-bar systems to these planets. Why do we have more interest in these systems? Because the relation in size between a super-Earth and an N-bar star is smaller, so it's easier to see this kind of objects while transiting these stars. Here, they recalculate the cumulative insolation by taking into account the saturation time, which is bigger than in other stars for N-dwarf. Then the burst that these stars are one of the most unstable, so it has a lot of burst, and pre-main sequence radiation. So N-dwarfs are stars that last longer in the pre-main sequence phase, so it's send more radiation to the objects, to the dust that is surrounding it. Okay, so they develop, as the line is already developed by Sangle in 2017, they developed this color map in the background, which is based in this relation between cosmic escape velocity and cumulative installation. Okay, the blue side is for atmosphere retained, and the red side is for atmosphere lost. We made this plot. You will see later to see how does it change with our new approach. What do we want to do? Okay, redefine the concept because it is, as you can see here, it is completely outdated due to this cosmic shoreline. It's give a really bad approach for us because only 6 exoplanets with the size of an Earth are probable to have an atmosphere, which could be, but it's not what we want to hear. So we have to find another way to make it more realistic or more affordable for us. Okay, then analyze this impact of rocky planet. That's why we develop other analysis in parallel with this ARM metric and improve this target selection. With all these three points, what we want is to establish a new hierarchy to make the proposal for James Webb, ELTs when they are in use, and Ariel mission, which will be like the companion of PLATO. Well, they are competing, but they will be companion in the end. Okay, how did we do this? Okay, the first thing is that luckily we have access to the exoatmosphere database from IAC, where they keep all the discoveries from planet characterization. So we can do a cross-matching with the list of planets discovered by NASA in NASA archive. So what we did is to make the cross-match between the planets we have with detections, no detections, and the planets we have none of them, and appears in NASA exoplanet archive will be non-static planets. Well, normally it's in the Neptunian desert because it's a desert, but well, it is what it is. And in that way, we get a really good survey of planets with detections, non-detections, and we can do like a better approach to this conception. Okay. For doing this, for defining an empirical cosmic shoreline, we have to determine which planets have an atmosphere. Okay, there are 3 planets that are good options because they have low escape velocity and high cumulative installation, so they should be the edge between having or not having an atmosphere. Okay, these are the 3 ones. GJ 1132b, which is controversial because it had in 2020, I think, or 2022, a really good, 2020, a good detection of, I think it was hydrogen cyanide, but in 2022 and 2024, in 2022, Jean with Enrique Payet came up with a paper denying it, and in 2024 they repeated this result with, I think it was with James Webb, and nothing appears. So it's controversial because one paper said yes, but other 2 said no. So we get it out from the opportunity list. All of these planets are, well, these 2 are super or in the border with subneptunian, and LTT 9779b, it's a small gas giant, probably a Neptunian or a small Jupiter, which it should be the best option, the more realistic, the safer, the safest. But the problem is that if we get this planet, which is a small gas giant, we get 55 Cancri out of the retaining atmosphere, and 55 Cancri is demonstrated that it has a secondary atmosphere. It's true that, well, the referee in this paper, we have sent this paper to the archive, told us, okay, but it's a lava world. But okay, but if it has an atmosphere, it has an atmosphere. It's not even if it's a lava world, it is what it is. So we make it to be 55 Cancri. It is a special situation to be the border. Okay, in the beginning it was Mars, and Mars has a tiny atmosphere, but it has an atmosphere. So now we can do whatever. This is the plot we get, where you can see the red dashed line is the original cosmic shoreline, and you see that it goes just in between all the new planets with detection. All in green, these are all detections, and a lot of planets stays out of the atmosphere retaining zone, so it makes no sense for us. So with the other option we had was the dotted line, black dotted, which is the same line as red with the same slope, but changing the 0 point to 55 country E. The problem is that in this way, items from the solar system that has no atmosphere fall below the line. All of these that has no name are dwarf planets or comets or things that has no atmosphere for sure. And what we did, okay, if the theory doesn't work, we are using the logic. So we make a bachillerato exercise. We get 2 points, define a slope, and say, okay, the solution is in front of us. We took 55 country E, we took Mars, and say, let's make it happen. Okay, we make it, and it makes sense. Well, that's everything we want. The planet number 1 is 55 country E, which is our target planet. Then Mars, and other interesting objects around the line, which are the more remarkable, is number 3, which is GJ 1132, which is what I mentioned. It should be out of the line, so it makes sense for us. Then number 6, which has a really good detection with James Webb, and the thing is, okay, it falls out of the line, but it could change because it was here before, but 2 weeks ago I refreshed the table of NASA and some parameters changed, so life is like that. So 1 week here, the next week here, so it could be whatever, but the thing is that it's a really good signal that there are 3 planets almost in line with our line, so it's really good for us. And other interesting objects are Pin-Side C, it's number 4, and GJ 9827b, which is here. So very good results for us. And as you can see here, LT 9779 should be a really more safer option, but for us it's good. Now the new line has these parameters. Now the relation the power is to the power of 6 more or less, and the 0 point is using 55 country and Mars with 4.19. Okay. Next thing, we repeated the results for PASS with the ARM, which is the background. You can see red, non-retaining, blue, retaining. Easy. Then we have, these are all these systems in M stars, but with names only in M dwarf and closer to us than 15 parsecs. Okay, so here are also well-known systems like all the TRAPPIST and all the targets that we had in the previous image. So you can see, and this is with the recalculated cumulative installation, okay? So here you can see, white line is the classical cosmic shoreline, which is really similar, the position with the previous one shown by PASS. Then the dotted is the classical, but moved to the 0 point of 55 country E, and our line, which is the empirical cosmic shoreline. Here you can see that in the white zone, L9859 falls in the white zone, which is really good because the white zone, as we understand it, should be a transition zone or uncertainty zone because it's not in the non-retaining, nor in the retaining. So if a planet with detection falls there, it's good for us. Even a planet with no detection means nothing because no detections could be because of the instrument, not enough visits from James Webb, the data from James Webb. Currently is a little bit controversial, and now with our empirical cosmic shoreline, there are good news for us because there are a lot of items that are below in the retaining zone, so it's really good. Here we have the first detection, which is LHS 1140b, and other targets that have been studied like TOI 2156b and several other options. Here, okay, if we want to establish a hierarchy, we have to study the 2 parameters that have been developed for James Webb, which are the transmission spectroscopy metric and the emission spectroscopy metric. Transition spectroscopy metric is based on, okay, it measures how fluffy your planet is, and it only uses radius scales, temperature, and masses between star and planet. So it's much more easy to calculate than the emission spectroscopy. Here you can see that are a really good, are 1, 2, 3, 4, 5, 6 really good options to study, because this is for primary eclipse. So here there are 6 objects that should be in the in future programs, like, well, not DDT program for this web because it studies secondary transit, but all the other stuff like when Ariel or when LTS come up. Then after this, well, these are obviously these are, I forgot to say, but these are the same planets that disappear here, okay? But just with this color bar for the TSM. After it, we wanted to make it more general, so we studied the ESM for the James Webb DDT program. Here you can see that was news for us, because here the mission spectroscopy metric is based on how the planet reflects the light, so you have to use black body equation and everything. The thing is that, okay, if these planets are all super Earth, it's really difficult that the mission is important enough to be detected. So here, instead of having 6 planets, we have 4 planets only. That should be interesting, because these 2 that don't have this metric good enough to be studied with to waste the time of James Webb. And apart from this, obviously, it would be interesting in both of them to study the planets that are close to the line, like GJ 486, like here. Okay, and here it is even better to observe it with the DDT program. Okay, there are some planets that has been added manually, like for example GJ3929b, which is the first target for the DDT program of James Webb, and it is out of the line, but well, I know what the result will say, but well, no. The good thing is that the week we published this paper, the result for this planet was released, and it's out of the retaining zone, and the plots were flat, but it means nothing, because right now the result from James Webb, it's controversial, but well, it's a good hint for us. After this, we were interested in, okay, from these planets and all other planets that are not only in M-dwarf, we are going to study the ones that are in ability zone. So these are planets that are with a radius lower than 2.25 and in temperature between 250 and 350. So we plotted the TSM for these planets to look for other interesting objectives and targets. So here it remains the old one that were in the previous, and if we go to these are planets farther than 15 parsecs, we get 1, 2, 3, 4 new targets that would be interesting. The problem is that, for example, K218b, it's well studied, and now they are coming up with a lot of papers. This is the planet of the detection of dimethyl sulfur. I think they were claiming that it was light there. It's not. Well, you know. And the most interesting for us should be TOI 1468C and TOI 1266C. I am Andalusian, sorry. And well, and Kepler 1652b. So this is for the TSM, and for the ESM, well, this is worse. It's normal, but we still can use the data, or we still can use these 2 to make a good analysis. Okay. What are the conclusions for this? Okay, we were able to establish empirical cosmic shoreline only using observational data to improve this hierarchy. We have a more optimistic outlook for future missions, because obviously having this, well, this with all of these objects that have not been studied yet is better than only having this, at least for me. Then this is a robust framework to establish which planets are more likely to be habitable. Well, we establish a new hierarchy in terms of using this paper or this study to for proposals or everything.
very much for that. Question?
Hi, thank you. Very nice presentation. I am very sad because I just wrote to a group of people that TRAPPIST 1E is like a likely candidate. Now you see that it probably doesn't have an atmosphere, so
Yeah.
change the
Yeah.
what we are going to say this Saturday in the
Yeah, the best
researchers'
from
night.
TRAPPIST, the best from TRAPPIST should be G or F because they are in this zone.
Why did we put E? This is not our topic, clearly. I was curious about two things. First, the cumulative installation,
Mhm.
then it's XUV, the IXUV. Does it mean that it only takes into account the UV radiation?
No, it takes the normal radiation, the normal insulation, and the XUV. Everything. It takes everything. It's
Okay.
but the equation is, I mean, the way that we calculate the cumulative installation is a little bit
No,
complicated.
complicated.
Well,
I was
it's
wondering-
not that complicated, but the thing is that the calculations are so easy because it's only the relation between semi-major axis ratio and luminosity ratio with the sun. So there are a lot of factors that we are missing and we should take into account. But for that, we need more data from asteroseismology or the behavior of the stars and everything. So there is a lag between. We should be more talkative between exoplanet people and star people.
I was wondering if there was some room for improvement there. I see that there is. And also, you were saying that the data from JWST is controversial. I want to know more about this. I didn't know.
Why? For exoplanets, it's a problem. It's saturated right now, James Webb, and you cannot believe any paper that came up with planets because it has probably 2 nights. And if you're observing something that has the height of an atmosphere like the Earth, you will see nothing. And in 2 nights, we'll see more nothing. And you will need like 10 nights or 1,000 nights to see anything. For example, for this paper they were claiming for these planets, they were claiming they found dimethyl sulfide or something like that. That was live, whatever they say. We tried in the group to replicate the results. No, it's a flat line. I mean, if your model and your results are able to be fitted by a flat line, it's a flat line. So you have a rod, a really nice rod, a rod.
So the problem is that there is not enough signal.
Yeah, you don't have the errors are right now too big. So you need a lot of nights. That's why the DDT program comes up. But the problem is that they are observing, I think, four objectives, and they are all bad objectives. For me, because they are observing this LTT 1445 instead of this. I don't know why. This, they are observing also this. There was other one, but I don't remember what was the other one. And they are all, even in the classic cosmic shoreline, they are even farther. So I don't know why they choose these objects, but well. They're supposed to constrain better what planet has or not atmosphere. I wish now they use this to make it better.
Are there some second order effects that make the shoreline not a shoreline but like a band? For example, the composition of the atmosphere of the planet, things like that. I wonder if you have the composition is a lighter gas, it's not going to be the same line for another planet with the same parameters but a more heavy gas atmosphere.
We have played with the idea of that the relation could be depending on the planet type, but it makes no sense because the planet type that is formed depends on the star. So we studied the idea of that the cosmic shoreline may change depending on the star type. The problem is that the planetary sample here, all of these, or more or less all of these, are ultra hot Jupiters, or Jupiters. So it's really difficult to claim anything if you only have a small sample of planet type. So you can do this classification by star type, but you need more planet type to be able to develop a really good cosmic shoreline. But I think in the future this will change, and probably we will have this cosmic shoreline for sections. In case of Jupiter's, it could be like this. Then for, well, in depending on the stars. In terms of, for example, from here to here, it could be like this. Then here it could be like this, and then if we go to smaller or less energy, it could be like more flat, and we can construct build a better way to classify it. But right now, this is what we have and what we could have, because here it's completely empty. As you can see.
Yeah, but precisely because of that, you cannot make a more precise line. Maybe it's better to work with a band or with a probability.
Yeah, that's why.
Because a line is going to be black or white. But the other, as you said, no, this planet was here and then moved there. Then it doesn't mean that it's become uninteresting now.
Yeah.
It means that maybe you have a distribution around that line.
Yeah.
It's your list of candidates. And
This
there
is
you can.
the idea of this ARM is to calculate the probability of having or not having an atmosphere, but obviously it has a bias based on the line, the 0 point that you establish and everything, because you have to mark a 0 to develop this ARM. So we need more data, but right now there is a gap between the instrumentation and what we want from Excellence. So we need more and more things.
There's also like the other edge of this region, because if it gets too cold, the gas will freeze on the surface.
Yeah, and will happen. I mean, if the cumulative insolation is so low, this is what happened for solar system items. Here, for example, Aries has an atmosphere, but it's too cold, so the atmosphere is more or less always there, but it's not that stable, and it's how do you say? It's sublimate. Sublimate? Yeah, sublimate. When it's closer to the sun, it has an atmosphere, but when it gets farther, it gets not completely lost, but really tiny. Yeah.
And there were some solar system objects which had a weird spectrum, and it was out. They were in a region where, among the common substances in atmospheres in the Kuiper belt, it was right at the edge of one of them freezing out and the other.
Yeah.
Didn't.
Yeah. That's the thing. The trans-Neptunian objects are complicated to put inside of here. That's why we try to work with them better known, like Titan, Mars, all the planets and Titan. This is Mercury, which makes sense that it's completely out of the line, and this is the Moon. So that's a very good thing for us. Here, I hear that there is a group in Oviedo that here will come up with a paper that says that Makemake, I think it's Makemake or Home, I don't remember, has an atmosphere, but probably it's the same. That like the same as Aries, that it's a transitionary atmosphere.
Questions? No? Thanks again, the speaker. You are dismissed.